differences? Okay, could you make sure you just, I see your mouse? Yeah, okay. Okay, very good. The next speaker is Renaud Boussarie. And so he has 45 minutes in total. So it's 35 plus 10 for questions. Is that correct, Masoud?
That's what I was.
Yes.
Okay, very good. If you could begin. Thank you.
Perfect. Thank you. So first, I'd like to thank the organizer and especially Masoud for the organization. And I would also like to thank Alina Chaika for her previous talk, because that's a great example, I think, of how CGC adjacent concepts like the plasma can be applied to heavy ion collisions. The reason why I'm thanking her for that is that, weirdly enough, for QGP phenomenology talk, I will not mention the QGP. The purpose of my talk is to give you an overview of the color glass condensate as an effective theory to understand how initial state correlations can lead to correlation in observables, and how it is used later on for heavy ion collisions and studies of QGP. I will leave up to you. My purpose right here is to build a theory from electron-proton collisions all the way to PA and maybe AA collisions in the CGC. And hopefully by the end of this talk, you would have enough tools to understand CGC talks and CGC papers about the follow-up topics. Because as you probably noticed, if you ever attended a CGC workshop or read a CGC paper, it's very easy to get drowned in equations because it gets technical quite fast. So my purpose is to simply give you the basic ideas and hopefully not too much technical theory of how the CGC works. So let me start now by basic small x physics considerations, because I will build my case up to the CGC starting from this simple physics. So how do we actually understand the Partonic content of a hadron? Now, on a theoretical point of view, one of the tools we have is perturbative QCD, which allows to actually factorize observables into Partonic sub-amplitudes that we can compute with Feynman diagrams simply, and the non-perturbative matrix element, which will then describe actually what's going on in the hadron in terms of partons. So the simplest case we can build here is how we access the Partonic content of a hadron by simply hitting it with an electromagnetic probe. So if I'm studying the total cross-section for EP collisions, there are two variables that are relevant to this observable. We have the center of mass energy S of the process, of course, but what will happen is that the proton will be struck by a very virtual photon whose virtuality will provide a hard scale. If this virtuality is large enough, we know that thanks to the smallness of alpha S at very high scales, this hard scale will allow us to use perturbation theory. This hard scale is also something we can understand as 1 over a transverse resolution. So if this virtuality is very large, then we will see point-like patterns here inside the targets. So the way we will usually draw the phase diagram for such a collision now is in terms of this q square variable and the so-called x variable, which is q square over s roughly. So in terms of q square and 1 over x here, this is the phase diagram. So as I said earlier, q is a transverse resolution. So at very large q, I will be probing point-like pattern in my proton. But if Q is still large enough for perturbation theory to apply, but still not so large, I will have non-zero transverse sizes for my partons. And something you can show, even it was shown even pre-QCD, that basically if you start increasing the energy, well, gluon exchanges will start to dominate. So, and if I increase and increase and increase the energy at some point, if nothing happens, I would see an infinite number of gluons with a finite size inside a finite size hadron. So that would break what's known as unitarity, but basically it would be an unphysical picture right here. So what happens is saturation effects. The fact that we have many gluons which have finite sizes means that their wave functions will overlap, and we will have some recombination effects between those gluons, which are known as saturation effects. Now, we usually divide this phase space into two subspaces. We have what's known as the moderate X phase, where Q square is very large and it's of the order of S, and the so-called small x phase space, part of the phase space, which is when Q square is much smaller than S. That's where the CGC would apply. But to build my case again, I will start with moderate X physics, because that's what's best known probably to people who studied perturbative QCD at some point in their career. Okay, so what happens in there is we have a hard scale, which allows us to completely factorize any observable into something we will compute with Feynman diagrams, what's known as the hard amplitude. And the other part in here is the so-called non-perturbative matrix element, which gives us, say, if you look at this diagram, you will compute Feynman diagrams with quarks, with gluons, and with photons, etc. But how these quarks and these gluons are extracted from the hadron is what's given by these Barton distribution functions. So this simplest example we have for that is the PDF, which gives you basically the probability to extract a parton, a given parton from hadron. And the interestingly, so you have PDFs for quarks and for gluons, even you can distinguish valence quarks and C quarks, etc. And if you start looking at smaller and smaller values of X, you can see experimentally that the gluon exchange starts to explode as predicted by theory. So you really do see that, you see this G over 10, it completely dominates. So if you simply decrease the values of X that you're probing, you see more and more gluons. I mean, these distribution functions really grows very fast. And so where you have many, many gluons in your target is where the CGC would apply. Okay, so let's go to this small X regime right now. Now the physics is a bit more complicated because of that. And I will introduce a bit of terminology. Just those are words that you probably heard at some point. So just to clarify, before QCD, there was an effective theory for hard interactions at very high values of S. And what was shown, it was known as the Regge theory. What was shown back in the days is that at very asymptotic values of S, you will exchange an effective particle which have the quantum numbers of the vacuum. Say you're studying gamma proton to gamma proton, for example, you'll have an effective particle with the quantum numbers of the vacuum, which is C+. That's known as the Pomeron. If you had, let's say, photon pion instead, you would have a negative C parity exchange here, and that's what's known as the Oderon. So those are the effective particles exchanged at very large values of S. That's pre-QCD. What the CGC provides is how we understand these particles in QCD, or more accurately in perturbative QCD. So let's just use naive QCD right now. How do we describe something with the quantum numbers of the vacuum? Well, the simplest thing you can build, of course, if you only have gluons, is two gluons on a color singlet state. Now, this is C+. It has the quantum numbers of the vacuum. So if you're building a Pomeron order by order in perturbation theory, then you would see that this guy is the so-called leading Pomeron. That's the simplest thing you can exchange. If you add an additional gluon now, you will have two contributions. It can be C+ or it can be C-, in which case you would respectively talk about the sub-leading Pomeron contribution or the leading Oderon contribution, and so on and so forth. We have quite a few formalisms that historically allowed us to understand the Pomeron and Oderon in terms of QCD. You know, the most famous ones being BFKL, of course, and BLV for the Oderon. But we now have a much more general framework, which are the small x semi-classical effective theories, which actually allow to resum all gluonic interactions into actual non-perturbative operators. That's the CGC is one of them. So how does this work? Now, let's consider now a photon hitting a proton at very large energy. Say the photon is moving along a plus and the proton along P-. This guy, P+ is roughly square root of S, P- is roughly square root of S as well. So to factorize now, I will actually simply separate the gluon fields. I only have gluon exchanges in T channel because we're at large S. And I will simply say, well, gluons which are slow, so low rapidity gluons belong to the proton, and large rapidity gluons belong to the photon. So I'm simply splitting my gluon field now between fast gluons belonging to the photon wave function and slow gluons which are exchanged from the proton. And now I'm boosting this picture to go somewhere in the rest frame typical for the photon. So these gluon fields from the proton are now completely Lorentz contracted into what's known as the shock wave right here. Because of this large Lorentz boost, which is of order square root of s, these fields have this extremely simple form, which is known as the shock wave approximation, where it couples along one Lycon variable, and it actually coupled all these gluon exchanges all occur at the same Lycon time, which is 0. So because it's Lorentz contracted now, we all have all these interactions at exactly the same point. And this allows us to build effective Feynman rules for these long lifetime partons here in this scattering, which is now instantaneous. Because of this large separation of Lycon times, you can actually very much simplify the Feynman rules for effective scattering. So if you look at one of the fast partons and how it scatters in the external field, you will see that because there is no time for any propagation between each interactions, which all occur at Lycon time 0, the propagators here are basically just simple phases, and you can completely exponentiate all the interactions with the gluon fields into what's known as a Wilson line, which is a path-ordered exponential of gluon fields. You can understand that as simply a color rotation. So you have a free propagation, and at Lycon time 0, you get dressed by an effective particle, which is simply color rotated, and this is the second propagation after Lycon time 0. So from there, you're building a factorized picture, which is now something you can compute with Feynman diagrams. So you have, instead of simple Feynman diagrams, you have effective Feynman rules, but the idea is still the same. You will just use perturbation theory here to compute the wave function of the photon and the propagation of its constituent in the external field. So this blue quantity here is known as the impact factor. That's what you're computing here with your Feynman rules. And now the way the target is seen as by the photon now is simply given by the action of those Wilson line operators here on proton state. So instead of parton distributions, which are very simple probabilities to extract partons, what we have now is this complicated color rotation operator striking here proton states. And this is how you can build the pomeron. If you simply look at these Wilson line operators and project them on the color singlets, if you symmetrize them, you get the pomeron. If you anti-symmetrize them, you get the odoron. And that's how you understand those in terms of semi-classical QCD at small x. Okay, so you have this complicated factorized picture. The point is to factorize it, we had to introduce some rapidity scale at which we would separate between those blue fields and those red fields, of course. And you have to get rid of this rapidity scale to some RGE, some evolution equation, right? And that is what the Balinsky-Jimok hierarchy of equation does. It allows you to lose the dependence on the factorization scale. So if I slightly modify my factorization scale now, I have some gluons that belong in the space between the rapidity, which was the previous one, and the new rapidity that I have. So those gluons used to be external classical gluons from the target, and now they are quantum gluons. So they are also fast, and they will also get dressed by the Wilson lines. So if I compare the evolution of a given operator, because I have these additional gluons that also scatter, we'll have more complicated operators because we are adding Wilson lines because of the gluon here. So what happens is we do not have one single simple closed evolution equation, but instead we have an infinite hierarchy of equation, which is known as the Balinsky-Jimok hierarchy of equations, because this guy evolves into a more complicated operator right here, which also has an evolution into something even more complicated, and so on and so forth. If you want to truncate this infinite hierarchy, the easiest way you can do that is to use the mean field approximation. Because if you look at this term right here, and you look now at the matrix element for this guy acting on the protons, in the mean field approximation, well, the action of the product is basically the product of the action. And that gives you a closed equation in terms of the action of the operators here on the targets. This is the well-known Balitsky-Kovchev equation. Now, I said mean-field approximation. Sometimes we use the word large NC limit because, well, you can think of those guys as scalar rotation. So saying that NC is going to infinity is basically the same as saying you're taking mean-field approximation. So you have this nonlinear term here in the evolution equation. And what this does is it takes into account the recombinations between two such guys. So you're now taking into account all recombination effects between the gluons inside the target. And that is what I call the saturation effect before. Okay, so we now know that something like that is bound to happen as we increase the energy. So how do we understand at which point this occurs? Well, that's where the saturation scale enters the game. And you can think of it very simply. That's even pre-CGC. If you look at the number of gluons per unit area inside the target, so if you look at this guy, this is the nuclear PDF. So this is the probability to extract a gluon from the target, and you divide that by the unit area for the target. So that's the number of gluons you will see in any area. And now the probability for such gluons to recombine is given by roughly alpha s over the Hart scale. And you will see saturation when you see recombination, which means when the product of these two guys is reaching 1. So this means that the saturation scale solves this equation right here. And you can actually see from results that give you the nuclear PDF and for estimates of the radius of the target, you can show that QS is roughly proportional to, so this is the mass number for the target, this is A, and X here is, as I said, this is 1 over the energy. So, So as I increase the energy or as I probe heavier and heavier ions, I will have larger saturation scale. So we'll start to see more saturation effects. And this will be one of the purposes of the electron-ion collider in the future. Okay, so there is some saturation effects that occurs at some points. And that's what the CGC will actually deal with and use. Just to sum up now, when it comes to electron-ion collisions, we're now in a phase of precision physics when it comes to that. The evolution equation is known at next to leading log accuracy. And we also know quite a few observables, very diverse range of observables at next to leading accuracy as well. So we know the evolution very precisely, and we know observables precisely, but there is one thing that I have been sweeping under the rug right now, which is, of course, how do these guys actually look like? We know how they evolve, we know how they couple to the photon, but how does this action of such an operator on the target state looks like? And this is what the CGC will provide. Okay, the CGC will give us the picture of how those guys look like inside a Hadron. So how does it work in practice? Well, very simply, you reverse the picture I have shown earlier. So instead of going right now to a frame typical of the photon, I will now boost everything to go to the side of the target right now. So I will look not as, the terminology is slightly different. So instead of using the term fast partons and slow partons, we'll use weak gluons and valence partons. But the idea is exactly the same. You're boosting everything. You're going to this new frame, which completely Lorentz contracts the gluon fields in a T channel. And now we again have this very large separation of lifetimes. So the lifetime of the partons inside the heavy ion right here is much, much larger than the scattering time with the target. So you have these very large separation of time scales, which I think is the reason why we use the word glass in color glass condensate. So now the wave function of the Hadron now is something you can understand as a collection of static color sources because of the separation of time. And we will assume that these color sources are classical random variables, and you will treat them with a weight function. And so instead of a wave function of a hadron, what you will understand now is that you have a weight function of a distribution of color sources inside the hadron. And that's the idea of the CGC. These guys are sources for the weak gluons in the T channel, in the sense that, as you saw in the previous talk, these gluons in the T channel are the solutions to the classical Yang-Mills equations with those static sources are as actual sources. So you will now solve classical Yang-Mills and you will understand what's going on in the T channel. So to understand now these target matrix elements that I have been sweeping under the rug in completely generic small x effective theory, now I will understand those as the averages of configuration of the sources rho here with this weight function and of the dynamical field that they generate here in T channel. So this very simple thing is now modeled with this complicated correlator here, but the idea is simply you are averaging over all these valence sources that constitute the Hadron wave function. Okay, let's look at the very textbook model, this beautiful McLaren-Venugopalan model, MV model. So if you look now at the heavy ion right here, this heavy ion, if you basically assume that, well, it has a nucleon and each nucleon is 3 valence quarks, then what you will see, you will have 3 A sources inside the heavy ion. Now, the typical radius of this heavy ion is a to the 1/3 times some parameter that you adjust for dimensions. And the transverse resolution, as I mentioned at the very beginning of the talk, is if you're probing this heavy ion with a probe of hardness 1/q², that's a transverse resolution. So now the probe is seeing exactly this number of sources, right? So you have the number of sources divided by the surface and multiplied by the transverse resolution. And that's the number of sources you will see. Now, this means that if you have a probe that's hard, but not hard enough for q² to be larger than a to the 1/3, basically, then you will be probing a very large number of sources. This means you can assume that this random distribution of sources, that you have a very random distribution of sources, which means the total colored charge here probe is 0. So you will set the average of one charge rho to be 0 in MV. Then you will assume this, make this additional assumption that if you have two sources, they are correlated under two conditions. First, they will build a singlet, and second, they are local. Okay, so you have these, this parameter lambda here is the correlation between sources that are close to each other. And then, well, typically you will use a Gaussian for the weight function. So what will happen is in the MV model, you will model these target matrix elements right here as the average over color sources given by this Gaussian here, which is a function of the correlation between two local sources. And that's how you can actually build some models for the action of matrix elements on a very heavy ion target. Now, there are several ways you can go beyond MV, and that's an ongoing topic of the CGC. Of course, you can add a transverse dependence in lambda. I think the previous speaker did have a transverse dependence in lambda. Or you can include also some higher point functions, or you can have non-Gaussian weight functions. I mean, there are many things you can do to improve the MV model, which is really a textbook model. So if you have a correlator of 3 rows, usually this provides what we know as an Odoron term. So that's one way to understand the Odoron, not in generic small x physics, but in the CGC this time. Okay, so that's for one hadron. Okay, now how do we deal with two hadrons colliding? And I think how I just presented the CGC should make it clear to most who are listening right now, because as I said, each hadron now is a collection of color sources. So you have two distributions of color sources right here colliding with each other. So if you look at any observable, so any expectation value for an operator, then to compute these in the CGC effective theory, you would simply, well, you have two weight functions, one for each hadron, and you have these dynamical fields that are generated on each side here. So these guys, is distribution of sources which generate dynamical field in one Lacan direction, and this guy is distribution of other sources that generate dynamical fields here in the other directions. And this way, you can build the generic expectation value for an operator right here in the CGC, simply using models for the distribution of sources in each hadron. Okay, so we have two different hadrons, we have two distributions of sources, so we actually have two different saturation scales, of course, because as I said, the saturation scale depends on two parameters. The mass, so A for each of these guys, and the energy, or actually the rapidity between those two guys. So depending on where I am here for my final states in rapidity space, I will more or less saturate each of the hadrons. And depending on how heavy each ion is right here, one of them will saturate faster than the other, or well, one of them will saturate before the other. So it's important to study where we are in rapidity when studying CGC observables. And the cleanest thing we know is the so-called hybrid factorization ansatz. If we're somehow very close in rapidity to one of the beams, say we're very forward in rapidity in the particles we're observing or interested in observing, then we can assume simply that the saturation scale here is just too small to ever lead to saturation effects. Because again, this is proportional to 1/x. So in forward rapidity, we can actually use the CGC to describe not both heavy ions, but simply one heavy ion. And the other one doesn't have saturation enough to be a dense state. So we will now use good old collinear factorization or QCD factorization to describe one of the guys, and the other guy will be described by the CGC. So this allows us to, by simply going to forward rapidity in our observables, to understand the projectile right here as a probe for the target and nothing else. So we will simply try to understand what's going on inside the target, even if we have a complicated heavy ion or PA, usually collision, because one of them will serve as a probe. So now we do have also next to leading order observables for such well, processes in hybrid factorization. So we do have some precision physics on the way right now. Now, of course, the whole purpose of this talk was not just to give an introduction to the CGC, although that's what it is, but it's also how to understand how the CGC can lead to initial state correlation effects, of course. So let's study a PA collision now in a hybrid factorization ansatz. So let's say we're studying production of a dye jet here in the forward region of the detector. So we have two jets right here, which provide a dipole of a given size R, and this dipole here will serve as a probe for the target. So we are measuring some small areas of some small domains of size R inside the target. And there's a very popular model for the CGC where the target actually contains a few domains where the color is canceled. So you have some domains of color singlets. And the idea is that if you're measuring the target with a small dipole, then there's a chance that you will measure a distribution of sources inside one of these domains, and those sources are then bound to be correlated. So in terms of observables, the small dipole is equivalent to having a back-to-back pair. So if you're studying dye-jet production for back-to-back dye-jet in the forward region of the detector, the idea in the CGC is that you will start to probe local correlations inside the target by looking at the correlation in the final states for such an observable. So that's one of the ways you will see correlations from the CGC. Okay, let's move out again of hybrid factorization. Because now, well, not all observables are in forward rapidity, first of all, but also because, well, it's an ansatz, so you don't have to use this ansatz, of course. Oh, sorry, this should be 1/3. I don't know why I didn't correct that. But so, yeah, the idea now is, let's study, let's say, PA. So we have one of the two guys right here is still much denser than the other. So we have one with very large saturation scale and one with a small-ish saturation scale for the collision right here. And we somehow, let's say, middle in rapidity. This is where what's known as Grasograph appears. So that's one of the more cryptic, maybe, tools that we have in the CGC. So if you ever looked at seen such diagrams in the CGC, I will try to explain now what's going on. So let's say I'm studying the double inclusive gluon production. So I'm looking at this, basically. We have two gluons somewhere here measured in the center. So we have to understand how these two gluons were emitted from the dilute projectile and how they rescattered on a dense target. So to do that, we have to compute how this operator right here, AAAA, so that's extraction of 4 gluons from the projectile, actually works in the CGC. So, well, there are quite a few assumptions that are made in the Grasograph to actually finally look like those diagrams here on the top, which are known as Grasograph approximations. So first, you will assume that these 4 gluons that you took from the projectile all came from different sources. So you're now studying the emission of 4 gluons from 4 sources in the projectile. So this is now how you simplify one of the correlators. The second approximation that will be made is that 2 of these gluons will build into a singlet. So instead of having AAAA, you're now studying the product here, AA times AA, okay? So you have to pair sources that will build singlet gluons. And this is what these guys here see, okay? So you're pairing this first source with the last source, or the first here with the second source. So that's how you see these structures right here. And the second assumption is that now you're scattering with the target with Wilson line operators, of course. And now you have 4 points again. So you have 4 gluons, 4 interaction points with the target in the effective theories. So you're now assuming again mean field approximation. So instead of having these 2 pairs, you will actually see 1 pair and 1 pair acting on the target. And that is again what builds these weird-ish diagrams that you sometimes see. Okay, so, and finally, these big dots that you see in here, that's the effective scattering dot. So what I showed at the very beginning of my talk was this effective Feynman rules that would dress up a fast pattern with a Wilson line. That's what those dots do. This is known as a Lipatov vertex. And that's basically telling you how these gluons that have been extracted from sources actually see the targets with these Wilson line operators. Okay, so this is the very basic Grasograph approximation. This is complicated enough by itself, of course, but you can go beyond that. First of all, by simply not taking the mean field approximations on one side or on the other, or you can stop using the iconal coupling. So instead of having this very simple shockwave picture for the coupling of the gluons with the target, you can use some corrections to this effective Feynman rule. So that's one of the popular topics right now, and many talks about CGC physics or papers about the CGC will give some correction to Lipatov vertices. So you have to understand simply this means that the scattering with the target is now slightly more complicated than it is in the usual CGC. And of course, there's another thing you can relax, because as I showed in this graph, you have assumed here that each source emits a gluon. But of course, you can have one source emitting a gluon that then splits into 2 gluons. And that's one of the corrections you can go. So overall, these graphs that you would see in many talks in the CGC gives you how correlation, local correlation between pairs of sources right here would lead to correlation between the gluons in the final state under given set of complicated diagrams given from simple assumptions here about how the CGC average for the projectile and for the dense target would go. All right, so I will move to my conclusions right now, because I think it built up to where I wanted to go. So just to sum up, the CGC is one effective theory that gives you how a dense target is probed by a hard probe. And this effective theory has been developed quite far, and we know right now many observables at one loop or next to leading graph accuracy. So we do have precision phenomenology right now on the way in CGC. Of course, that's one type of precision, but there's also things that you can do beyond the actual textbook MV model. As I mentioned earlier, you can go beyond the Gaussian, you can add some higher point correlators and so on and so forth. There are many things you can correct in the target models before you can actually study the whole perturbative side of things that we know now precisely. And from the CGC, you can understand correlations, initial state correlations. So how local correlations in a given domain structure in heavy ion can lead to final state correlations in the observables, or from Grasograph, you can understand how local correlations between sources in the CGC can lead to final state correlation in observables. Now, there are a few typical topics as well right now that are popular. Is the reason why you could go beyond MV or beyond the Grasograph is to see odd harmonics in CGC. This has been a problem and a very interesting question to study. But also spin effects. If you're completely iconal, so if you use the path of vertex for your CGC computation, you will see that there's no longitudinal spin effect at all taken into account. So how we include spin effects in the CGC is a very popular topic right now. Okay, so I hope I introduced the CGC clearly enough for you to understand now any CGC talk, or at least have the understanding of what's going on beyond the last equation. So thank you for your attention.
Thank you very much. You actually finished early, and so I didn't interrupt you with the 5-minute warning. So I open up the discussion to questions, please. If I can ask a trivial question, Renaud, back in at the very beginning where you showed the BFKL and the other limits, I just had a question which I figured out way at the beginning where you show an x squared and q squared in x space.
This?
Yeah. So the reason when you go to the right that the dots get smaller in DGLAP is because you're going to larger q squared, of course.
Yes.
And then, but then why do they? Then, oh, I see. And they're the same size as you go up in. Okay.
Oh yeah, I didn't increase the size in, or that would have been a mistake. Yeah.
Okay. It was a very nice talk, if I may say. It was very clear. And if you could go to where you had terms of higher order in row corrections to the MV model.
Mm-hmm. Yeah.
And then I see there's one question, but let me just ask. So are these terms suppressed by 1/NC or?
I'm guessing if you square those, then the d squared would be suppressed, but I don't have a quick answer to that.
Yeah. No.
Yeah,
that's fine. In any case, there's a question from Mubarak Al-Ghatani.
Yes.
If you could go ahead.
Yes, if you can go to the last slide, your summary, please.
Mm-hmm.
About spin effects, do you know how important that, considering the spin effects in a CGC? At least in heavy ion collisions, how important?
Yeah, I understand the question. So there have been some efforts in heavy ion collisions to understand how subiconal effects actually affect, especially odd harmonics. So if you look at the work by Artinoluk and Armesto, etc., you will see that. What was not considered is how much of these subiconal corrections are spin effects that I know of. This was not the focus of that. So in that sense, I cannot answer how spin actually affects the CGC in those observables. But I can turn the question around. How much does the CGC and saturation physics affect the spin of hadrons? And there has been decades of work by Yuri Kovchegov and collaborators on this topic. And it seems that saturation is an important component for spin. So we can probably also infer that spin is important for saturation as well.
Okay, thanks.
Very good. Are there other questions? I think you gave such a clear talk that everybody understands everything.
It was either very clear or very unclear.
No, it was very nice. No, it was very nice. It was a very nice discussion. It was a very nice discussion.